sample space associated with a random experiment is a set of all possible outcomes of an experiment, and it is usually denoted by S. Any subset E of the sample space S is called an event. Here are some examples. Sample space of rolling a die is S equals to 1, 2, 3, 4, 5, and 6. A die has 6 faces, and each face of a 6-face die denote 1, 2, 3, 4, 5, and 6. The number of possible outcomes is 6. E is equal to 2, 4, 6 is an event which can be described in words as the number is even or the event of even numbers. Another example is tossing a coin twice. The sample space is S equals to head head, head tail, tail head, or tail tail. E is equals to head head, head tail is an event which can be described in words as the first toss result in a head.
The probability of an event A is the sum of the probabilities of the individual outcomes of which it is composed. It is denoted as P of A. The following formula expresses the content of the definition of the probability of an event. If an event E is equals to E sub 1 and E sub 2, and therefore E sub key, then P of E is equals to P E sub 1 plus P E sub 2 plus P E sub key. The following figure expresses the content of the definition of the probability of an event. Since the whole sample space S is an event that is certain to occur, the sum of the probabilities of all the outcomes must be the number 1. In ordinary language, probabilities are frequently expressed as percentages. For example, we would say that there is a 70% chance of rain tomorrow, meaning that the probability of a rain is 0.70. We will use this practice here, but in all the computational formulas that follow, we will use from 0.70 and not 70%. So let's have an example. So example number 1. A coin is called balanced or fair if each side is equally likely to land up. Assign a probability to each outcome in the sample space for the experiment that consists of tossing a single fair coin. So the solution will be, with the outcomes labeled H for heads and T for tails, the sample space in the set, so S is equals to H and T. Since the outcomes have the same probabilities, which must add up to 1, each outcome is assigned probability 1/2. Second example. A die is called balanced or fair if each side is equally likely to land on top. Assign a probability to each outcome in the sample space for the experiment that consists of tossing a single fair die. Find the probabilities of the events E, an even number is rolled, and T, a number greater than 2 is rolled. So the solution will be, with the outcomes labeled according to the number of dots on the top face of the die, the sample space in the set will be S is equals to 1, 2, 3, 4, 5, and 6. So since there are 6 equally likely outcomes which must add up to 1, each is assigned probability 1/6. Since E is equals to 2, 4, and 6, thus P of E is equals to 1/6 plus 1/6 plus 1/6 is equals to 3/6, or 1/2. Since T is equals to 3, 4, 5, and 6, such that P of T is equals to 4/6, or 2/3. The sample space of a random experiment is the collection of all possible outcomes. An event associated with a random experiment is the subject of the sample space. The probability of any outcomes is a number between 0 and 1, so the probabilities of all the outcomes add up to 1. The probability of any event A is the sum of the probabilities of the outcomes in A. Conditional probability is the probability of one event occurring with some relationship to one or more other events. For example, event A is that it is raining outside and it has a zero point 0.3 or 30% chance of raining today. And event B is that you will need to go outside and that has a probability of zero point 0.5 or 0 or 50%. A conditional probability would look at these two events in relationship with one another, such as the probability that it is both raining and you will need to go outside. So the formula for conditional probability is P sub B over A is equals to P. So example number 1. In a group of 100 sports car buyers, 40 bought alarm systems, 30 purchased bucket seats, and 20 purchased an alarm system and bucket seats. If a car buyer chosen at random bought an alarm system, what is the probability they also bought bucket seats? So step 1. Figure out P of A. It is given in the question as 40% or zero point 0.4.
Number of outcomes both in an event and in the sample space. The first rule is the fundamental counting rule, which is also known as the multiplication rule. It states that if an operation can be performed in n sub 1 ways, and if for each of these ways, second operation can be performed in n sub 2 ways, then the two operations can be performed together in n sub 1 times n sub 2 ways. For example, let's say that you are buying a new car where there are two body types of car and five colors to be chosen, and there are three models of car to be chosen. Calculate the total choices in buying a car. To solve this example, simply use the multiplication rule formula, which is n sub 1 times n sub 2 and so forth. First is the two body styles of the car, so 2, and then we multiply it with the total of available colors to be chosen, which is 5, and then the number of um, the number of models of cars to be chosen, which is 3, so that makes it 2 times 5 times 3, which means you have a 30 choices in buying a new car. Next is the permutations. A permutations is an arrangement of all parts of a set of objects. Another useful calculation is the number of ordered sequences of the element of a set. Consider a set of elements such as S is equal to set of A, B, and C. A permutation of the element is an ordered sequence of the event. For example, A, B, A, B, and C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. Those are all the permutations of the elements of S. The number of permutations of n different element is n factorial, where n factorial is equal to n times n minus 1 times n minus 2 times so forth times 2 times 1. In some situations, we are interested in the number of arrangement of only some of the elements of a set. The following result also follows the multiplication rule. The number of permutations subset of R elements selected from a set of n different element is probability of R and n is equal to n times n minus 1 times n minus 2 times and so forth times n minus r plus 1 is equal to n factorial over the n minus r factorial. For example, a printer circuit board has 8 different locations in which a component can be placed. If 4 different components are to be placed on the board, how many different designs are possible? To answer this example, we need to identify first. So, each design consists of selecting location from 8 location for the first component, a location from the remaining 7 for the second component, a location from the remaining 6 for third component, and a location from remaining 5 for the fourth component. Therefore, we have the probability of 4 to 8 is equal to the components that we identify earlier, which is the 8 times 7 times 6 times 5. Or you can also write it as 8 factorial over 4 factorial, which results to 1680 different designs are possible. And the last one is the combinations. Another counting problem of interest is the number of subjects of R elements that can be selected from a set of n elements. Here, order is not important, unlike the previous one. The number of subsets of size R can be selected from a set of n elements is denoted as n and R, or C, n, and R, and it can be written as n and R is equal to the n factorial over R factorial times n minus R factorial. So, for example, a printer circuit board has 8 different locations in which a component can be placed. If 5 identical components are to be placed on the board, how many different designs are possible? So, in solving this, we need to identify which is the n and which is the R. So, in this case, our n here is the 8 different locations, and our R would be the 5 identical components. So take note, 8 is the n and the R is the 5. So we use the formula of the combinations, which is nr is equal to n factorial over r factorial n minus r factorials. So we're just going to input the values that we identified. So we put the 8 in the numerator, which is the n factorial, and r factorial, which is 5 times n minus r factorial. So eh, so 8 minus 5 is 3. So we just simplified it here, so which makes it 5 factorial times 3 factorial. So 8 factorial over 5 factorial times 3 factorial is equal to 56. So that's it. It's very simple.
So today we're going to talk about the probability distribution. So a probability distribution is a function of a discrete variable whose integral over any interval is the probability that the random variable specified by it will lie within that interval. And now I'm going to discuss to you about one of the examples of the probability distribution, which is discrete distribution. So a discrete distribution describes the probability of occurrence of value of a random variable. A discrete random variable is a random variable that has countable values, such as a list of non-negative integers. Thus, a discrete probability distribution is often presented in tabular forms. So here is our example problem for the discrete probability distribution for us to understand further. So, example 1, flipping a coin 4 times, and the event here is getting tails. So, in flipping a coin 4 times, we're going to get the probability of getting tails. So, here, so its first possible combination would be HHHH, and also it could be TTTTT. And if we're going to count the sample space of the combination here in tossing a coin 4 times, it would be equal to 16. So our x is equals to 0, 1, 2, 3, 4. So there could be a chance of getting 0 tails, 1 tail, 2 tails, 3 tails, and 4 tails. So we're going to count how many possible chances we would be getting 0 tails, 1 tails, 2 tails, 3 tails, and 4 tails. So in getting the 0 tails, we have 1 chance. So 1 would be, so our x is px equals 0 would be 1 over 16, because there are 16 possible outcomes, and one of that is that, and so on. So that's all for today. Thank you.